Let us get example. Let us get example direct. Our wonderful beam. We will start with EA times this general beam. Here is general beam. Oh, bar, sorry. This is general bar or general beam. d2u of x by dx squared plus p of x equal to 0. What I can write here direct, I can get the same differential equation, EA times d2u of x by dx squared, this differential equation, plus p of x. This part is equal to 0. What I'm going to do it, I'm going to multiply it by any weighting function. I'm going to multiply it by any weighting function. Any weighting function. Here, any weighting function. And I will integrate all of this over the domain. This is a domain integral because my domain is stand from x equal to 0 to x equal to 1. The differential equation part itself is equal to 0. So this is equal to 0. And now I'm going to use integration by parts to swap this differential operator from applying on u. This differential operator is applied on u. I want to move it to be applied on u asterisk. This is a trick. So I'm going to choose this term. Can you see this term? Only. Because I don't want to get bothered with this term. I will add it at the end. So this term, how many functions that I have? I have two functions. I have the first function, the u of x, this part. And I have multiplied by this part. Okay? So what I'm going to do, I will use this one as a first function. This is the first function. And this is the second function. Okay? Why I'm going to use the first function? Because if you look at this, if you look at here, we will start with the first function as the second function. So we'll end up here times the integral of the second function. Here is the integral of the second function. So I want to apply the integral on the highest derivative. So I'm going to choose this one as the second function. So the first function is u asterisk. Here it is. Times the integral of the second function. So I integrated here du of x by dx. I integrated once. Okay? I don't want to forget the EA. Okay? I integrated once. And I will apply this from 0 to L, a boundary integral, minus integral from 0 to L, the previous integral, which is EA times du of x by dx times the derivative of the first. And this is the first function. So here du of x by dx. So this is the first step. The first step. Okay? So I removed one of the derivative from u and I move it to u asterisk. Again, I'm going to take this term only. Again, and I'm going to use this function is the first function. Again, this is the first function. And I'm going to use this one as a second function. I'm going to do it again. Why I'm doing again? Because I want to remove all derivative from u. So this part will end up to, so the first function, which is du asterisk by dx. Okay? I don't want to remove EA times the integral of the second, which is u of x, minus integral of the previous integration, which is u of x, times the derivative of the second function, which is EA times d2 u asterisk by dx squared. So now I moved everything from all differential operator from u to u asterisk. Let us write it now, the final form we have. We end up to here two boundary integrals, u asterisk here, u asterisk here, times EA of du of x by dx. This is the first part here, and the second part here, we have it here. We forgot here to write it between 0 and L also. This one minus here, so it will be minus EA times du asterisk by dx times u small of x, and all of that between 0 and L. Okay, minus times minus equal to plus integral u of x from 0 to L EA d2u asterisk by dx squared. We shouldn't forgotten the last term here, which is integral from 0 to L p of x times u asterisk equal to 0. Okay, so we end up to this very nice equation. So actually what we did is to move our differential operator. Instead of it is 2, we have differential equation of order 2, we end up to differential equation of order 1 actually. Here is u of x d by dx u of x, and we have u of x here. Okay, we don't have any other higher, we don't have any higher derivative anyway. So actually this is what we call it the strong form. This is what we call it the strong form, because we have our function u of x is differentiated twice, and the last equation here we have, this is what we call it the weak form. Why we call it the weak form? Because our derivative now is weakened by 1. Okay, this is great, but we'll carry out another step. Still, I can choose any function I want. I can choose u asterisk as any function I want. What I want to do it now is I'm going to choose u asterisk as a fundamental solution of this equation. I'm going to choose EA times d2u asterisk by dx squared equal to minus delta of x minus xi. As far as I put x minus xi, so this one ought to be x minus xi. Okay? And I know from here that u asterisk of x from here is very well known by integration, and we did it before, and u asterisk of x minus xi equal minus half sine of x minus xi times x minus xi. So if my choice here for u asterisk to be this equation, so this part I'm going to write it in black. This one will be x minus xi because I added. This one will be x minus xi. This one will be x minus xi, and this one will be x minus xi. The second part, it is very well known that this part here, all of this part will be minus delta of x minus xi. It is very well known, once we have the delta function inside integral over the domain with a certain function, this is called the filtering property. If we have integral from 0 to L, u of x times the delta of x minus xi, it will end up to u of xi. This is called the filtering property for the Dirac delta, and you can prove it very easy. You can prove it even using Laplace transform. It's not a problem. So we will end up to very nice equation. We'll have it here. We have u asterisk of x minus xi times this part. I'm going to join these two together. It will be f of x, because this is f of x, minus I'm going to join these two parts together again. It will be f asterisk of x minus xi times u of x integrated on the boundary minus u of xi from the filtering property plus integral over the domain from 0 to L p of x times u asterisk of x minus xi equal to 0. And this is the direct integral equation. Why it is the direct integral equation? Because we don't have phi. You remember from last time, we used to have integral equation u of x equal u asterisk of x minus xi times phi. And f asterisk, f of x equal sigma f asterisk of x minus xi times phi. We apply boundary condition, we solve to get phi, and from phi we get the superposition of the effect of phi's to get the value of the values. So we solve first for phi, and after that we get the internal points and the boundary points. But here we don't have phi. We condensated phi from the equation. We removed the phi from equation. Okay? So at the end of the day, we ended up to have very, very nice integral equation, and we have direct the solution. How many xi here we have? Actually, we have any number of xi. We can choose xi anywhere. We can choose xi inside the beam. We can choose xi outside the beam. We can choose xi on the boundary. So where is the unknowns? Anything you like. But the problem, how can I apply the boundary conditions? How can I apply the boundary conditions? The trick is to choose xi at the points of the boundary conditions. Once you choose xi at the points of the boundary conditions, from this equation you will be able to incorporate boundary conditions inside this equation. If you choose, I will get another slide and I will write it again here.